based on symmetry, and which is, a generalization of the Landau paradigm. And I realized from some of the questions that I should have said a little more about the usual Landau paradigm, which I didn't explain. So let me say a little bit about that now. So this is the basic statement that phases of matter can be labeled by how they represent their symmetries, and a consequence of this is that a consequence of it is that the degrees of freedom should be swept out by the symmetries. And so sort of conservative assumption based on this is that if we have some phase of matter that has some symmetry G, the degrees of freedom that we need to include to describe it should form some representation of that symmetry. And so the basic strategy to sort of weaponize this perspective is to introduce at each point in space a degree of freedom that transforms linearly under the symmetry. Don't think of it as some microscopic description. Think of this degree of freedom as some coarse-grained magnetization averaged over some small patch of space. And let me call it a strategy. So introduce 5x, which let's think about the case where the symmetry is just Z2, and the idea is that this is some linear representation of G. So in this case, that means that under the symmetry, 5x goes to minus 5x. And then the next part of the philosophy is, well, let's try to write an effective action for this degree of freedom. And because there need be no other gapless degrees of freedom, gapless degrees of freedom should be swept out by the symmetry, so that if this is the symmetry, this should be the only thing. The effective action for this degree of freedom should be local. Right? There are no other gapless degrees of freedom that we're integrating out that would produce a non-local effective action. And so it means we can write some effective potential, which should contain all possible terms. Here, okay, maybe the effective action should contain all possible terms consistent with the symmetry. And so what can we write? Well, we can arrange them in an expansion in decreasing relevance. So there can be a constant, which doesn't matter. There can't be a linear term because that doesn't respect the symmetry. There can be a quadratic term. There can be a quarter term. Then there can be some derivatives. And so from this point of view, we see that, so if the parameter u is positive, that's true in some open set of the space of possibilities, then the phase diagram looks like this as a function of this parameter r. For r positive, the potential looks like this. So this is phi, this is v of phi. And for r negative, the potential looks like this. And somewhere in between, something dramatic happens where r goes through 0. There's a point where the gap closes. So everywhere here, the system is gapped, and there's one ground state. The number of ground states is equal to 1. And everywhere here, the system is gapped, and the number of ground states is 2. And this quantity, the number of ground states, I think you'll agree is always an integer, right? It's always an integer, so it's something that can't change continuously as we vary the parameter, and therefore can be used as a label on the phase. So we know without having to check every possible path between this point and this point that this state, a state over here and a state over here, have to be in different phases. There has to be a phase transition in between them where the number of ground states maybe isn't so well defined because there's a continuum above the ground state. And that's the only way in which this integer can change. And so therefore, this number of ground states which came from the symmetry considerations is a possible label on the phase. So this is the basic strategy by which this procedure can give us labels that distinguish phases of matter. Okay. So last time I defined this notion of a p-form symmetry in an attempt to generalize this perspective on the world, which, I don't know, we can denote like this. So the p indicates the form degree, g is a group, and so this is, think of it as some set of u alpha of sigma. Sigma here is a d minus p minus 1 dimensional closed surface. and alpha is some element of G. It could be discrete, it could be continuous, and these are topological operators. Yeah, topological in the sense that wherever you put them in the path integral, it doesn't matter. You get the same answer as long as you don't move through a charged operator, which is some W of C supported on some p-dimensional locus in spacetime. And a charged operator, by definition, transforms like this. Okay, let me write it like this. U alpha of sigma, W U alpha dagger of sigma, and an operator of definite charge means that the transformation law is like this, where now I need to tell you how lambda is. So lambda here is a p-form. It's a thing I can integrate over this p-dimensional locus. I need to tell you how lambda is related to alpha and sigma. Yes? Global symmetry. What is it? I'm not sure what you mean by it shouldn't have support anywhere. So the... Yeah. Sigma is, yeah, actually, maybe it's better to think about some constant time slice. Let's say this is t equals 0, and then sigma is some locus inside that constant time slice. It's not. Okay, so right, good. Let me try to clarify some things. So right, so that's a zero form symmetry, right? And okay, so the perspective that I tried to convey last time is that we don't need to think about the transformations of the fields, right? Not every symmetry involves some transformation of the fields. The thing we care about is this collection of symmetry operators that are topological. The fact that they're topological is, that's how to say it. It's a slight strengthening of the statement that they're conserved. And now the idea of higher form symmetry is that we generalize, we relax some of the conditions that we're imposing on those topological operators. An ordinary zero form symmetry, the topological operator, as you say, is supported everywhere, right? It's a codimension 1. It's supported on a codimension 1 locus in space-time. So the generalization that we're making here is that instead, a p-form symmetry operator is supported on a codimension p+1 locus in space-time. So that means that it's here and not here. Yeah. So this notion of local symmetry is a confusing thing. And so part of the reason that this is a different idea than that is that this operator, the symmetry operator, you should think that it's not acting on local operators, right? It's not doing something to the field somewhere in. Exactly, it's acting on these higher operators that are supported on higher dimensional things. So for one form symmetry, it acts on strings. Sorry? Well, good. So that's exactly the point I wanted to make. Lambda is a closed p-form. So this is a p-form here. So this is the statement that you're making. Lambda is a closed p-form, meaning that it's constant on that manifold. That's correct. That's correct. Yeah. Okay. Good. And how is it related to these other objects? Lambda is equal to alpha times, let's say, a delta function on sigma. So alpha is just some number. This delta function on sigma is closed because sigma doesn't have a boundary. Great. Okay, so maybe actually I'm going to talk about some physical consequences of higher form symmetries, but maybe let me pause for a moment and talk about a physical consequence of this generalization of symmetry, even in the case of zero form symmetries. So this is saying that the symmetry parameter is a p-form, which we integrate over the p-dimensional locus here, which is closed, right? So in the case for p equals 0, this says, lambda p is a zero form, but it's a closed zero form. So let's think for a minute about what's a closed zero form. Usually we think that just means it's a constant. But this is a brief interlude. I want to describe an interesting physical consequence of the fact that this is the right way to think about symmetries. So perhaps some of you are familiar with the phenomenon phenomenon of coarsening. So this is a situation where we take, say, a bunch of spins on a lattice, and let me draw dots for up and nothing for down. And so take initially some t equals infinity configuration. Think of it as a t equals infinity configuration of the Ising model, right? Meaning you just IID pick the spins to be up or down, and then evolve it by Monte Carlo evolution, by Glauber dynamics. Monte Carlo dynamics, but with a temperature less than Tc, a temperature so that it's in the ordered phase. And so what happens? Well, the thing that happens is eventually, if you do it long enough, it goes to either all the spins are up or all the spins are down, right? There's the fact that in the ordered phase there are two equilibrium configurations means that there's it has some choice to make that depends on the initial conditions. Okay. That's coarsening. And I guess this is a place where I wish I were using slides, because then I could show movies of it, which the movies look really cool, because these things, the regions of the upspins grow, that they try to shrink the length of their domains, at least to very nice movies. But now consider the following other version of this problem. So that here I was talking about coarsening in this convex domain that I'm drawing, just this square. But suppose we instead start with coarsening in a configuration in a domain like this. Right, so the spins only live in this bottleneck shape. Now, if we do this, the thing that happens, it's very easy to simulate, is that instead of 2 equilibrium configurations, there are now 4. There are 4 because if we form a domain wall here, a domain wall in this neck of the bottleneck, it tries to shrink its length, but in order to go away, it has to grow for a while. So this is a very long-lived metastable state, because the process by which it goes away is some instanton where it has to go over this big barrier. So there's this, and then of course they could all be up or all down. So now there are 4 equilibrium configurations, and why is that? Well, the reason for this is that there's an approximate symmetry that protects the lifetime of these metastable configurations, which is if I shrink the bottleneck completely, so that instead we were just sitting 2 disconnected domains, and then obviously there are exactly 4 metastable equilibria. And that's because this system has a larger symmetry. It has a larger symmetry because I can independently flip the spins here and here. A closed zero form on this space has to be a constant on each of these domains, but it can be a different constant on the 2 domains. And so the approximate generalized zero form symmetry is what protects these 4 equilibria. Okay. End of this interlude, which I think is amusing. Okay. All right, so we were in the middle of a spirited debate with Eduardo about the meaning of symmetry breaking. And I had said that my definition of symmetry breaking forcing what to be in this example? It's like, yeah, you're somehow making it near the first order transition by making this domain wall very cheap. That's right. That's right, but except we're totally not, right? The bulk physics is the same, yeah. That's right. It's a literal bottleneck to coarsening. Okay, so I define spontaneous symmetry breaking to mean that there exists a ground state that's not an eigenstate. Of G, of the symmetry. And it's a fact that this is true if and only if the system has long-range order, by which I define there exists a charged operator with a non-zero expectation value in that state. And there were reasonable objections that this definition of symmetry breaking is sort of happening directly in the thermodynamic limit, and it's a bit dangerous to talk about the global symmetry operator that acts everywhere in the thermodynamic limit. But I feel okay about that because of this equivalence, Indeed, it may be difficult to prepare this ground state that I'm talking about unless you do something else. But I feel okay about this because by this equivalence relates it to a statement about charged operators that you can tell in a finite region, that you can distinguish in a finite region, and what I'll say later about entanglement bootstrap makes it clear that this is something that you can diagnose locally. Yeah. Yeah, that's this.
Well, it gives you the square of that.
What? Yeah. Great. So about the word local. So in the case of zero form symmetries, a charged operator is by definition local. In the case of higher form symmetries, a charged operator is supported on a p-dimensional locus. And so, let me just say a little more about this definition in the relation to exactly what you're saying. One way to characterize this long-range order is indeed by studying this sort of correlation function in the limit when x becomes large, right? It doesn't have to be infinity; it just becomes large. And if this decays exponentially, then there's no if it decays, there's no long-range order, and this is no long-range order, and that's to be distinguished from if instead it goes to a constant. The constant is interpreted as the product of these expectation values, right? So that's what this is. I think this is what you're. Yep. That's this statement. Okay. Sure.
But the object that you're going to compute from that is invariant under the plane. Because whatever, say, imagine that the symmetry was U1, then you get an amplitude times a phase, and if the other one will give you an amplitude times the complex quantity of that phase.
Mm-hmm.
So this diagnostic does not detect that phase.
It doesn't tell you where you are on the vacuum manifold. Sure. Sure.
You know, you have the general vacuum.
Sure.
The same here. It's true, you cannot tell whether it's
Yeah. I'm not telling you which ground state we're in. Yeah, that's right. That's that's exactly what I'm trying to do. Exactly. Yes, I completely agree. Okay, so now I want to reinterpret these two lines in the following way. I want you to think about this object, this charged operator on 2 points, as an operator supported on a zero sphere. A zero sphere is the set of points x such that x squared is equal to 1, right? Or x squared. It's a stupid definition, but it's 2 points. It's this point and this point. Anyway, it's these 2 points, x and 0. I should have done 1 and minus 1, I guess. Let's say x squared equals r. And this is a statement about the limit when the zero sphere becomes large, right? When the zero sphere becomes large, either the operator has a non-zero expectation value or not, or it decays. And so for a p-form symmetry, the analog of this condition is simply we study some expectation value of some charged operator. That's the analog of this, where C is think of this as some p-sphere. And then the question we ask is, in the limit when this is some p-sphere of radius r, in the limit when r becomes large, what is the behavior of this as a function of the size of r? And there are essentially two possibilities. One is it could decay, like the area of by area here, what I mean is the volume of, I guess the minimum of the volume of some region R whose boundary is C. I guess I should really call it volume, but I think in the case of one-form symmetries, this is really an area, and that's it's called area, exactly. So that's why I don't want to call it volume. And in this case, we say there's no long-range order. And in contrast, instead, if it goes like the perimeter, well, let me just write perimeter of C, by which I just mean the surface area of the curve C, whatever dimension it has, then we say there's long-range order. And in what sense is that true? Well, if this expectation value goes like something that's proportional to, we can think of this as a product over points in C of some number, I can redefine W, so let W twiddle be, let me just think of it as, so W is something supported on C. I can redefine it by, at each point on C, I just multiply by this number, right? This, whatever this number is, W of C, I guess I want to multiply by the inverse of the number, in which case, this W twiddle approaches 1 in this limit. So which part are you objecting to? I agree. And the difference is that in this case, it's not. It's really not. There's a very important difference between the two cases. So I totally agree with you that you can't divide by anything to make this go to 1. And the difference is that in this case, the thing we're doing is local along C. Right? We're making some change of our operator. Think of it as a Wilson line, right? The thing we're doing. That's right. That's right. A Wilson line is just the trajectory of a massive particle, and this is just describing some renormalization of the mass of the particle. What's the objection? In this case, yes. Correct.
I would say that is a spontaneous symmetry because the dual order parameter, the dual, the top loop is what is getting the constant low. So there is, you are looking at the incorrect.
Okay. This is great. This is a nice point. So whenever you break a symmetry, you're restoring the dual symmetry. Yeah, this is a deep point that you're making. I agree. But my statement here is about G. What I'm saying is that in this case, G is not broken. I agree with what you're saying. No. But the same phenomenon happens there. If I spontaneously break a zero-form symmetry, I restore that means the disorder operator has 0 expectation value. Yeah, the same thing happens there too. So this is not different between zero-form symmetries and higher-form symmetries. There's a scale in both cases. This thing has units of volume, and this thing has units of area, right?
Exactly. So morally, in that convention that you are taking, you are saying that the spontaneous symmetry breaking is happening, in the other way around. It's better to say that the phase of confinement is something that is spontaneously breaking some symmetry. Because it has a scale and there is something that...
Okay, you're adding information here. So I'm not talking about any particular gauge theory. I'm making a general statement about higher form symmetries, and I totally agree with you that whenever this happens, there's some other operator you can define that has an area law, and whenever this happens, there's some other operator you can define that has a perimeter law. That is some added information that does not in any way vitiate what I'm saying here. I agree with the perspective that you're saying, but what I'm saying is not wrong. I'm just saying, I'm making a statement about whether or not the symmetry G that we're discussing here is spontaneously broken. And I think you agree with me that in this case, G is not broken, and in this case, G is broken. Sure, it depends which of the states you're in. You can take some convex combination of them, you'll get... yes, sure.
And then you say, well, the fact that it's non-zero labels a phase, but the actual value tells you where on the phase you are. And by doing this, you're legislating, you're always in some...
Wait, where in the phase?
Equal to 1.
The magnitude of the Landau order parameter doesn't really have any meaning. It has no universal meaning. It does not. It does not. That's some microscopic thing that you're saying you arbitrarily define your spin to be 1 or minus 1. This is not universal information. Yes, yes, yes.
As you approach the critical point, it will scale in some way, and that depends on the scaling dimension of the operator.
Of course I agree. Okay. The disagreement here is merely about goals. At this moment, I'm trying to ask a very coarse question. I'm trying to just identify the phase, right? I'm trying to give a clear criterion for the meaning of the phase. You're asking a much more sophisticated question about the approach to the phase transition, which is not what I'm talking about right now. That's a statement about the behavior deep in the phase. Indeed, if we want to talk about phase transitions, which is a much more sophisticated thing that I'm not going to talk about right now, the things you're saying are relevant. Okay, I'm going to move on now. That's because if we can redefine the operator in this way, it decays. That's right. Yeah. So this is area law. This is perimeter law. Yes. Okay. I really don't think this is controversial. Okay. So I promised to reinterpret topological order as spontaneous symmetry breaking. And let me explain how that comes about. So what is topological order? Well, we said that topological order, a symptom of it, is that there are ground states. There's a ground state degeneracy where the ground states are not related to each other by any local operator. Instead, they're related to each other by some extended operator that describes the transport of the topological charges of anyons. And therefore, they're locally indistinguishable states. Those operators that transform the anyons are topological. We can interpret them as exactly this kind of symmetry operator. And so this says that there's one reference ground state, and then we can make another ground state by acting with this topological operator, and it's a different state. So that's exactly this criterion. It says that there exists a ground state that is not an eigenstate of the symmetry. Acting with the symmetry operator, you get a different state. So that's the basic idea. There are a few subtleties. Let me exemplify the idea. Maybe the simplest thing to do is to start with the BF theory that Fiona introduced. So let me just give two examples. So an action for the torque code involves two gauge fields, which I guess maybe we can be general. So let's do it in d dimensions. Let's think about the torque code in d dimensions. I think maybe let's restrict to the case where it's the one-form torque code. Let's think about the ZP one-form torque code. And so what's the action? It's P over 2 pi integral of B wedge dA, where, so I'm in capital D dimensions, so if A is a 1 form, then B has to be a D minus 2 form, so that altogether this adds up to a D form. So this is a generalization of this BF theory. And in this theory, the following objects, I guess I'm calling this sigma, e to the in integral of sigma of B. So sigma is some D minus 2 dimensional locus. So that's something I can integrate B over. And I call them U and V. U, N, and Vm. And C is a curve here. This is just the familiar Wilson line. So these operators are topological in this topological field theory, unsurprisingly. The interesting thing really is that this topological field theory is the low energy limit of some very well-defined lattice model in which we can identify what these operators are in the lattice model. And but there's an interesting fact about these operators. So because from the point in life of this Chern-Simons term, of this BF term, is it says that A and B are canonically conjugate variables, right? B is like the momentum of A, so they satisfy a canonical anti-commutation relation, which implies that that these operators Oh, and by the way, I guess I should say, you could think about B as a Lagrange multiplier that says that P times dA vanishes, and that means that actually only the case where these are between 0 and P minus 1 are independent operators. And, okay, and so we can think about the commutator of these guys, the group commutator. I call this one N and this one M. If I change the order here, I get a phase. And what's the phase? It's the intersection number. The 1 over P comes from this P in the commutation relation. It's the intersection number of sigma and C in space. So if here's sigma and here's C, here you see they intersect at a point. And this is a picture of space. It's the number of times they intersect. And so this algebra, I guess, it's very similar to the algebra of x and z, sigma x and sigma z. If P is 2, it just says that they anti-commute. And an important fact about this algebra is that it has no one-dimensional representations if P is bigger than 1. So meaning that if I have a state which is an eigenstate of V, if I act on it with U acts on it as a raising operator that changes the eigenvalue of V. Okay, so there's a slightly funny thing happening here. So one way to think about the algebra I've written here is that U is a collection of symmetry operators, and V is a collection of charged operators, right? Actually, this equation says that V is charged under U, according to the definition I gave here. I could have called V W. Maybe that would have been better. Okay, and the extra ingredient there is the fact that both U and V are topological. So the extra ingredient, the important extra ingredient is that if the charged operators are also topological, it guarantees that there's topological order. So yeah, the key ingredient here is that the charged operators, well, I don't know, we can think of them as either U or V, actually, it doesn't matter, by some duality transformation, are also topological in this example. So that's not automatic from this definition, right? So U has to be topological, but a priori W can, need not be. The extra ingredient here is that the charged operators are also topological. There's another point of view on what I've said here, which is we could say, this is G equals a one-form Z D minus 2 symmetry where the charged operators are topological. Or another point of view is we could say that the symmetry is actually a D minus 2 form symmetry times a 1 form symmetry, that both U and V are symmetry operators, if this is also true, but with an anomaly. Say again? There's no U1 symmetry. So this is an example that has a discrete higher form symmetry, which we could regard either as, okay, we could also say, no U1s here, no, yeah. So this is, ZP gauge theory. Right, so there are two perspectives. Either there's a 1 form symmetry or a D minus 2 form symmetry where the charge operators are topological, or there's this larger symmetry with an anomaly. So why do I say there's an anomaly? Well, I said yesterday that a higher form symmetry with P bigger than 1 is abelian, right? But here you see there's this non-abelian algebra, and the way to think about that is it's a projective representation of this abelian algebra, right? So this is the algebra they're supposed to satisfy. They satisfy that up to a phase which makes it much more interesting. I'll make a comment a little about what precisely we mean by an anomaly of a higher form symmetry in just a minute. Let me give one more example, another example. Still topological. Yeah. The U and V you can deform however you want. Yeah. The anomaly is just this phase. Yeah. This is a great question. This is what I thought for a long time, but it's not true. And I'll give a explicit counterexample. Yeah. So that you see that the anomaly is very important for this implying topological order. right? So this algebra is the thing that implies the topological order. And the anomalies are, if this weren't there, then we wouldn't need to have a ground state degeneracy. Yeah, so let me give one more example, and then I'll explain what I mean by the anomaly, and then I'll explain the counterexample. Let's just think about the theory of the Laughlin phase. K over 4 pi integral a which dA in 3 space-time dimensions. It's very similar. The idea now is that now there's just one set of operators, which are the Wilson lines. I can put an M here. And these, because now AX is the canonical conjugate of AY, this implies that UM of C, UN of C, they fail to commute with each other. I guess let's call them C prime, e to the I, 2 pi mn over k, intersection number of C and C prime of the things in the other order. Which one is M? This one is M. So in this case, there's a ZP, ZK, one-form symmetry with an anomaly, right? Obviously, the ZK group is just this, and this phase is an anomaly. So let me explain a little more what I mean by an anomaly of a one-form symmetry, and then I'll talk about this very important loophole. Quantum mechanics. It's hard. So okay, we can't talk about higher form symmetries in 0+1 dimensions, right? The difference between a higher form symmetry. Yeah, indeed. That's the same algebra satisfied by these. Yes, that's correct. Yes. That's exactly this description. Yes.
Right, but you don't go and put them on the same footing by claiming.
Why not?
Well, but the question is, what is that symmetry that's anomalous in the quantum mechanics?
Yeah, it's just a representation. You have a charge operator, and then the phase can come because it has a representation.
Right.
So calling it an anomaly is kind of strange.
Well, what would you say about this case? In this case, the charge operator is the symmetry operator. Exactly. Yeah. The charged operator is the symmetry operator in that case. Yeah. Yeah, I think it's not different. That's what I'm doing here, right? It's a Gaussian theory. Yeah.
Then you make a distinction between the symmetry generator and the observer.
If you wish. That's this perspective.
What you're saying,
Yeah.
or you're trying to put them on the same footing, so to speak.
What distinguishes them?
Okay, what is that symmetry? Quantum mechanics, what is that symmetry that is anomalous?
I would say in that case, the operator has some statistics.
Yes. I agree.
We can call it anomaly, and that's nice.
Yeah, so let me tell you the reason I call it anomaly. Yeah, there's a very, very simple reason, which is what do we mean by anomaly? Recall, I said yesterday that a good way to think about anomaly is anomaly of a symmetry G is an obstruction to gauging. And so now we have to ask, what does it mean to gauge a one-form symmetry? Right, so this, the simplest case to think about is, what does it mean to gauge a one-form symmetry? The simplest case to think about is if it's a continuous symmetry, right? So that we actually have a current. So suppose we have some current that satisfies this conservation law. In the case of a one-form symmetry, it's a two-form. Gauging it means I add to my action a term which is like J mu nu times some field, B mu nu, and I make B a dynamical field, right? So this is like a two-form gauge field that couples to my current, and then integrate over B. Integrate over B. Right, so this is now no longer a background field. And what am I doing when I do that? Well, essentially the thing I'm doing is, if I add this to the action, that means in my path integral over whatever fields I have, there's whatever the action was before, and then I'm adding this term, which is like integral of the current times some B. And this thing here, if I fix B, is exactly one of the symmetry operators. So the thing I'm doing when I gauge the symmetry is summing over all possible insertions of the symmetry operators. these U's. In the case where the symmetry is continuous, we also have to sum over non-flat B fields. But for discrete symmetries, it's really just exactly summing over the insertions of the symmetry operators. And so what are the symmetry operators in this case? The symmetry operators are the world lines of the anyons, right? I guess maybe I didn't make that entirely clear from this point of view. So yeah, what is this thing? As Eduardo was saying, this is the trajectory of one of the E/3 quasiparticles through space-time. And so to gauge the symmetry, the thing we're instructed to do is proliferate the world lines of these anyons, to condense these anyons. And so in this case, this is the same as anion condensation, which is a subject about which Fiona wrote a very nice review. And the basic fact is that in order to condense a particle, condensing a particle means that the many-body wave function, these are the positions of the anyons, is 1. It means it's some number. Eduardo might object to me writing 1. It's some number. It's some constant. But in particular, it has Bose statistics, right? If I exchange R1 and R2 in this function, I get a plus sign. So the only case where we can condense an anion is if it's a boson. This statement here, as Eduardo helpfully pointed out, is the statement that the Laughlin quasiparticle is not a boson. It has 2π/3 statistics. We can't condense the Laughlin quasiparticle, therefore we cannot gauge this symmetry. This is not anion condensation. It's not anion condensation. No, I understand what you're talking about. But that's not anion condensation. That's a different thing. It's the field that you're condensing there is a boson. Yeah. Nope. You're condensing a boson in that case. Yes, that's allowed. Yeah. So, but I'm making a very simple point here, which is that you can't condense non-trivial anions, and that's all. That true? Yes. That's also true. Yes, that too. Right. So this is why it's not a bad idea to call this an anomaly, right? Because it's an obstruction to gauging the symmetry. Yeah. Great. Okay. So I promised to explain a subtlety about this statement, which is why I've emphasized this anomaly. A subtlety, which I learned from a paper by Shimon and Castelnuovo. And these are the people that made the counterexample and the people that pointed out that it was a counterexample. So okay, maybe let me just say that let me just say the statement that I'm trying to make, which is that spontaneous breaking of a higher form symmetry, of p-form symmetry, by itself is not sufficient to imply topological order. I at one time thought it was. It is not. Exactly because of the intuition that Horacio mentioned, that there should always be an anomaly. But these folks, Huxford and Youngbeck Kim, studied the following counterexample. It's actually very simple. The Hilbert space is the same as that of the Torah code. So we put spin 1/2 on the links of a cell complex on the square lattice, and the Hamiltonian is a deformation of the Torah code. It looks like sum over vertices of some star operator. Weirdly there's a plus sign here, and a sum over plaquettes of BP of the plaquette operator. The plaquette operator is exactly the same as in the Torah code. The difference is this. Here, let me call this Q. The difference is the star operator is a deformation. Let me call it I. Vertices I so this means the links that are neighboring the vertex I of ZL minus sum over links that are neighbors of it of X. So this is the usual star operator. We deform the star operator by this extra term that depends on Z. So these things no longer all commute with each other. So it's a slightly more complicated model. It's and when beta goes to 0, it's just the Tor code. Okay, so it's a deformation of the Tor code. So clearly at beta equals 0, it has topological order. But it has the following funny properties. They don't commute. They don't commute. Yeah. So it's the Qs are not generated. You hurt me. You hurt me by saying this phrase. Right. They no longer commute with each other. That's correct. That's correct. So yeah. Okay. Let me first draw the phase diagram. And the way I'm going to describe the phase diagram is by telling you what the TEE does. So the topological entanglement entropy was mentioned by Shinsei. It's the subleading term in the entanglement entropy of a ball, which is there's some area law term minus the TEE, which at a fixed point, the TEE is the log of the square root of the sum of the anion of the squares of the quantum dimensions of the anions. So in particular, if this is not equal to 0, it's a definite signature. Shinsei used the phrase smoking gun of topological order. Sure. Oh, no, but if you act, it's possible to act with certain antagonistic finite depth circuits to make it a little bigger. Right? There's this phenomenon called spurious TE. No, you can actually, a computer scientist could come and choose the finite depth circuit so that it messes it up even for arbitrarily large regions. It's quite annoying. But however, the minimum value that this thing obtains upon acting with arbitrary finite depth circuits is this universal quantity. Yeah, hopefully there's no one around who wants to come and do this, so we don't need to talk about it. Okay, so here at beta equals 0, it's the Tor code where the answer is log 2. Right, the Tor code has 4 anions of quantum dimension 1, so this is equal to 4, the square root is equal to 2, the answer is log 2. Oh, I used two conventions for the logarithm in the space of one blackboard. Okay, here's what happens. It stays log 2 until some special value of beta c, and then it goes to 0. So in this phase, there's no topological order. So far this is not, of course if you deform the thing, you can eventually destroy the topological order. That part's not surprising. The interesting thing is the following. For every value of beta, for any given a ground state of the Tor code, let's call it ground state of 0, I can define ground state of beta, which is obtained by some simple thing. You just act with the product of these operators on the links on the ground state of the Tor code, is a ground state. Is a ground state of this H beta. So it still has a ground state degeneracy on the torus. Even this is for all beta, right? For all beta. That's the first fact. It still has a ground state degeneracy here, despite the fact that the TEE is 0. Okay. On the other hand, it's still, for all beta, it's still true that yes, that follows from this statement. For any ground state of the Tor code, there's a ground state of this system. Right? So this has 4 ground states. I can do this to each of them. I get a ground state. It's very weird. Okay. Furthermore, for all beta, the one-form symmetry generated by the product of the z's, this is a symmetry, commutes with H beta, is broken. What I mean by that is that there's a charged operator with a non-zero expectation value of it, I'll call it VC. I'm not going to say exactly what it is. It involves a product of x's. It has I don't mean just not zero. It has a perimeter law. It has e to the minus beta length of c. Okay, so this one-form symmetry is spontaneously broken for all beta. Right. So here we have ground state degeneracy, and we have spontaneous breaking of a one-form symmetry, despite the fact that there's no topological order in that phase. Now, okay, so here's where it gets even weirder. For beta bigger than beta c, Sorry. I don't think that's true. I don't think that's true. So sorry, hold on. The important thing here is that this model has a one-form symmetry where a charged operator under that one-form symmetry has an expectation value. In the confined phase, that doesn't happen. Yeah. Right, but that's not a charged operator under any symmetry. Yeah, that's the difference. Yes. Sure, that's the phase diagram Eduardo was talking about. So, okay, so indeed, what Eduardo was just asking was, suppose instead, I don't know, let's call it HG, is the Torah code Hamiltonian plus, sum over L of, let's do ZL, right? That's what you're asking, right? And the phase diagram there looks like this. Here's topological order, here's no topological order. So I claim that in this phase, this doesn't happen. Here, there's no spontaneous breaking of, so this one form symmetry is still there, but it's not spontaneously broken. The expectation value of the charged operator is area law. Yeah, that's the difference. That's why this is more pathological. Okay, so here's the resolution. The resolution is that for beta bigger than beta c, there's a zero form symmetry that's spontaneously broken. The degenerate vacua are locally distinguishable. That is, they spontaneously break the zero form symmetry, which is just generated by product of z. Just flip all the spins. And they have different expectation values. They have different magnetizations. And so you can distinguish them. So here's the summary. Here's the summary. The requirement of topological order is not only that you can get from one ground state to another one by acting with a non-local operator. It's that you also can't get from one ground state to the other by acting with a local operator. Right? You see, that's a stronger condition. So yeah, the lesson is that the fact that ground state 1 and ground state 2, the fact that you can't get from, so the fact that you, in some basis, the fact that local operators don't take you from one ground state to the other, in some basis, is not sufficient. Yeah, it is not sufficient. Yeah, so this is an example where there's no anomaly. Yeah.
The problem is we insert Q in the Hamiltonian
Q? Oh, wait, do you just mean this?
In reality, this actually is a gauge theory, so it's in some gauge, the unitary gauge.
You mean the ordinary Torah code?
Yes.
I totally agree.
When you do this, essentially, what happens is the term that you're calling the product of the excess, not the sum, is the product of the excess.
Yes, you're right. Thank you. Yes.
That is actually the generator of local gauge
Sure.
variation. And then you add
Yes.
a term in the Hamiltonian that is not invariant. So you bring the gauge limit is explicitly wrong. Sorry for insulting your sensitivity, but that's what one would say. And the only symmetry that remains is just the global zero form symmetry.
But it's not. But nevertheless, topological order emerges for any beta less than beta c. So you're not just completely destroying everything. Yeah.
That's because you can always think when you have terms that break gauge invariance explicitly, is because you have fixed some gauge. You can always write it in the gauge invariant way. Fine.
That won't change the physics, though. Yeah. Okay. So. Pure SU2, Yang-Mills theory. I think it's trivially gapped. I think so.
So it's not topological.
I don't think so. There are other gauge theories which confine, which do have topological order in the ground state, but I think not in that example.
Yeah, but I mean, you have the center thing.
No, but you need to, if you move out by the center.
No, but I mean, you are saying topological order as a spontaneous symmetry breaking of
One form symmetry. Yes, yes.
this does some generalized symmetry. Set 2.
Yeah, I think it's not spontaneously broken in that example.
If it is spontaneously breaking for the top loop or for the Wilson loop, one of those happens here. So there are some lines operators that have expectation value 1. Expectation value 1.
Right, because you can think of the confined state as a
So this is because
No, but it only has one of those symmetries, right? It only has one one-form symmetry.
the Charles symmetry.
let's talk about this afternoon because these are dual things. If you have one symmetry, the other is there. So it cannot be that you have only one. This is a real problem, I think, in the terminology.
There's a question of which ones are local operators. There's a very important distinction about. Yeah. Okay. Yeah. So I think, but there's a very definite question, right? So if the theory you're talking about is one we can put on the lattice, right, and study very explicitly. The question is how many ground states does it have if you put it on a torus? And I think in the example of pure Yang-Mills theory, the answer is 1. Yeah. No. No, there's one vacuum. I think there's one vacuum in that example. Yeah. Let's talk about it more later. Yeah. Okay, good. So here, the goal of what I was saying here is to say that we can understand topological order as spontaneous breaking of a higher form symmetry. Now I'd like to ask the following question. Let's move on to the next example. Why is the photon massless? Sorry? No, I'm saying you need the anomaly to get topological order. So the example shows that you can have spontaneous breaking of a higher form symmetry with no topological order. Yeah. Exactly. In this case, in this phase over here, there's no longer an anomaly. Yeah. I mean, maybe better to say the thing that was anomalous was the combination of these two, this thing. These two one-form symmetries, and in that phase, part of this part doesn't emerge. Yeah. Good. All right, so what do you think? Why is the photon massless? So I said that if we have gaplessness in a phase, that's something we need to explain. What protects the gaplessness of the photon? You're trolling me. Yes, that's right. So that's not the right answer, because it doesn't mean anything. It's not a symmetry. It's not a good explanation. Any other explanations? Yeah. So I claim that a better explanation is that it's a Goldstone mode. It's a Goldstone mode for a spontaneously broken continuous one-form symmetry. And so Eduardo said that there's no Goldstone theorem for higher form symmetry, so let me show you that in fact there is. It may not be exactly in the form that you want, but there is one. So let's suppose we have a continuous p-form current. So we can write it as let's assume that there's a current. I guess this is actually a slightly stronger assumption. I'm going to assume, not only that there's a p-form symmetry, but that it has a current. Then this implies the fact that it's a symmetry means that there's a Ward identity. The Ward identity, it says that d star j is basically 0. It's basically 0, except if it's near a charged operator. This is a Q. There's some contact term. Right, of course, and there's of course plus whatever other charged operators there might be around. Think of this as a statement about the OPE between this object and and the charged operator. This is, yeah, another way to write the statement that W is charged. This is, again, the Poincare dual of C. And so let's suppose that we're in the broken phase. So in the broken phase, let's think about, so that means that W, and let's normalize W. I won't write the twiddle, but I'm gonna say that we normalize it so that its expectation value is 1 in the broken phase. It doesn't, the actual value that we put won't matter for what I'm gonna say. And let's take C to be a copy of a plane, R sub P, that I'll draw like this. An infinite plane of which I'm drawing only one of the dimensions. And let me consider a Gaussian surface surrounding, we're surrounding that. So this is some sphere, it's a D minus P minus 1 sphere. And let me call the ball inside it B. So this is a D minus P ball, and the point of this ball is that it intersects C exactly once, right? So in particular, this delta function is going to have support if I integrate over that ball. And now let's integrate. Let's just integrate the both-hand side of this word identity over that ball and see what we get. I'm assuming that this is a symmetry. Yeah, this is. I'm assuming that it has, a P-form symmetry. I'm assuming that it has a P-form symmetry. U1 P-form symmetry. In the example of electromagnetism, J is like the field strength. That's right.
But you're also assuming that there is a dual U1, or it could be, I mean, you could have a McGreevy and you have only U1.
Could be just one form symmetry. Yeah, I don't assume both. Yeah. Okay. Theory has to be abelian. So, okay, here's my assumption. I'm not talking about gauge theory. I don't know what a gauge theory is. I'm assuming that I have this operator is topological, and that there's some charged operator that has an expectation value. That's it. That's it. Right. Yeah, exactly. Okay, so let's integrate the both-hand side of this equation over B. Right, integrate over B, the both-hand side of that equation. And what we get on the left-hand side is W times integral. We can integrate by parts. Integral of star j, and on the right-hand side we get just W, right? And now let's take the expectation value. Let's take the expectation value. Okay, right. Let's take the expectation value of both sides. And the thing, and maybe I'll make one further assumption. I'll make one further assumption that the integrand here, I'm going to assume that expectation value of j on the sphere, I don't know, it's a function of r and theta, where theta is this coordinate. I'm going to assume that it doesn't depend on theta. Okay? The problem is, has a symmetry under that rotation. And so what we get is expectation value of j of r times w of c is some constant. Oh, yeah, okay, here we can generalize. It can be any constant c, is iq times that constant, divided by the radius of the sphere. Sorry? Did I write a c? C. Oh. That's a little c. It's a little c, sorry. Okay. Sorry. There are too few letters. Okay, so this is the conclusion. The conclusion is that these two operators have a power law correlation. The only way that can happen is if there are gapless degrees of freedom. That's it. It implies the presence of a gapless mode. Okay, so now let me explain how to think about what the gapless mode is, and let's do it by analogy with the one-form case. So in the zero-form case, zero-form case. As I said, if we have a symmetry, the right thing to do is to couple to background fields, so that as we add to the Lagrangian some term that's like J mu A mu. Let's think about the zero-form U1 case. And if the symmetry is spontaneously broken, there's a Meissner effect, right? It says that the effective action for this A contains a term which looks like A squared, integral of A squared, where A is our background field. Right, this is, yeah, I like that. Say again? Yeah. Well, okay, that's a great point, right? I agree this should be gauge invariant. How can we make this gauge invariant? In fact, the only way we can make a gauge invariant is by adding a degree of freedom such that the effective action is actually d phi plus a, where phi goes to phi plus lambda when a goes to a minus d lambda. So that's gauge invariant, and let's give a name to the coefficient. Let's call it 1 over 4 pi g. So 1 over 4 pi g is the superfluid stiffness. It's just the definition of that coefficient of the effective action. So let's redo this for the one-form case. Maybe we could do, okay. Let's do the one-form case. Same logic. I add to the Lagrangian a term, which is couples to a background B field, and then if it's spontaneously broken, that B field gets a mass. It contains a term which is integral of B squared, and the only way to make that gauge invariant is if there exists some dynamical degree of freedom, which I'll call little a, where the effective action is a function of little a and b in the following combination. So what I mean by b here, b squared is b wedge star b, and the thing that goes here is dA plus b wedge star dA plus b. And the coefficient here, the coefficient here is 1 over 2g squared, is the analog of the superfluid stiffness. Now you see b is something that we put there just to learn something about the theory. We get to pick what b is. We could set b to 0 if we want. And if we set b to 0, you recognize this is the Maxwell term. And the superfluid stiffness happens to be dimensionless. It's the electromagnetic coupling. Okay. So that's the idea. Mm-hmm. We counted. There's exactly a photon. It has two polarizations. You're right, and I think there's an interesting set of generalizations to consider. Suppose we have some larger higher form symmetry, and we spontaneously broke it to some. Okay, you're defining on a lattice. I don't know. So there's this important restriction here that I'm talking about. The higher form symmetries I'm talking about are abelian, right? And
So suppose, the special case of the U1 gauge theory.
Oh, the gauge group is not related to the higher form symmetry, though.
No,
right?
I know, but in some sense I always associate that with the special property which of the deconfined phase of the U1 gauge theory.
Yeah, it's a bit special, I agree.
In principle, it goes to 5 dimensions.
5 dimensions. Why are we talking about 5 dimensions?
Because there will be phase transition in 5 dimensions. There is no symptotic freedom. And there is a phase transition between the confined and the deconfined.
A first order transition, yeah. Okay, we don't need to get into that, sorry. Yeah.
But there will be 2 phases.
Yes.
There will be one phase that will be deconfined.
Okay.
Say take SU2 gauge theory, for example. Will be deconfined in 5 dimensions.
Okay.
And will be confining as well.
I don't know how to describe that in this language yet. Yeah. We can try to figure it out.
Allow you to count, is there an analog?
I don't know. That's an interesting question. Yeah. I think there was another question up there somewhere. No? Okay, no. It was an optical illusion. Okay, so One very concrete thing that we can do with this, which I think I won't do in interest of time, is, so I mentioned that this non-relativistic QED, take a collection of non-relativistic fermions and couple them to the electromagnetic field, has this exact higher form symmetry. And more generally, such a description it's a good idea. Anytime we have heavy charges, and one thing that this implies is what are called soft theorems for scattering amplitudes involving a bunch of charges. Let's say n charges plus a soft photon. So soft photon means its momentum is small, and the statement is that as q goes to 0, there's a very definite statement about the form. So this is n charges, of charge qi, so this epsilon is the polarization of this photon, and momentum pi, epsilon dot pi over q dot pi times the amplitude for n photon. So this is the amplitude without the photon. So there's a very definite statement about the form of the amplitude in this limit where the photon is soft, and this can be derived just from this point of view. And this is from a recent paper by Para-Martinez from last month. I don't remember the number. So that's I think a very nice concrete application of this perspective. It leads to some very very quantitative statement. Okay, to be fair, people knew this from other points of view before, but I think it has some nice generalizations. Okay, so let me say a few words about infrared issues and UV issues associated with higher form symmetries. So last time I said something about spontaneously breaking a zero form symmetry, a continuous zero form symmetry in two dimensions. And I was talking about spatial dimensions, but Eduardo immediately said you can't do this because of the Coleman-Morgan-Wagner theorem. And it's worth mentioning that that theorem has a generalization to higher form symmetries. And we can prove the theorem all at once. So the idea is, suppose we spontaneously break a higher form symmetry. As a consequence of this argument, it means that there's this Goldstone mode, and then we can ask whether the fluctuations of the Goldstone mode destroy the order that we thought we had, whether there's an infrared divergence in the expectation value of exactly this Wilson loop, right? So whether setting it to a constant is consistent, or whether the fluctuations of the Goldstone mode are inconsistent with that. And so this expectation value we can write as a path integral over the Goldstone mode. It's governed by the Maxwell action. And then there's the insertion of this A. And by the way, this could be any P form. It doesn't have to be a one form. You see, actually everything I wrote here could be true. If I add some more indices here, would be true for P forms. Just interpret A and B as higher forms. And this you see is a Gaussian integral, which I invite you to compute at your leisure. And you can see that it's equal to this L is the size of is a infrared cutoff on the spatial volume, and then it's multiplied by this momentum integral, where k perp are the directions perpendicular. This is the perp direction, perpendicular to the Wilson line. And so you see that if the number of dimensions is not big enough, this is d minus p here. That's exactly the important point. The number of transverse dimensions is the thing that determines the size of the infrared fluctuation. So it says if d minus p is less than or equal to 2, there's an infrared divergence, which destroys the order. So this is the condition for, so you see it agrees, if I set p equal to 0, it agrees with the familiar theorem. For one form symmetry, 3 space-time dimensions is the smallest it can be, which is consistent with the fact that in 3 space-time dimensions, some funny things happen in gauge theory, like Polyakov confinement. Though that's actually a different effect than what I just described. Okay, so this is about the infrared. Now let's say something about the UV. So I hope to have convinced you on this blackboard that the photon is a Goldstone boson for some higher form symmetry. It could be, let's say, you know, in real life, there are electrons, there are charged particles, and so the electric one-form symmetry is explicitly broken, but nobody's ever seen a magnetic monopole, or actually nobody's seen more than one magnetic monopole. And so we can say that it's a Goldstone boson for the magnetic one-form symmetry. Now suppose there are magnetic monopoles. That means, so if there are magnetic monopoles, then the current, oh sorry, this one's called the electric one, sorry. The current is non-zero, right? The thing that goes here is the current density of magnetic monopoles. And so if there exists a magnetic monopole, however heavy, it means that the symmetry that I said, that for which the photon is supposed to be a Goldstone boson, the symmetry that's protecting the masslessness of the photon is not a symmetry. Do you think that means that the photon has a mass? Does the presence of arbitrarily heavy magnetic monopoles imply that the photon has a mass? Now, a reason that you might think this is, in the case of zero-form symmetries, like so think about pions, for example. Pions are pseudo-Goldstone bosons for some zero-form chiral symmetry. Right? The reason they're so light is because if we ignore the masses of quarks and the coupling to electromagnetism, the chiral symmetry is an exact symmetry that's spontaneously broken by QCD, and the pions are the Goldstone bosons. On the other hand, quarks do have mass, and so they're not exact. It's not an exact symmetry, and that means that the pions get a mass, right? So by analogy with that, wouldn't you think that this means that the photon gets a mass if we explicitly break the symmetry? So this is a place where the analogy between zero-form symmetries and higher-form symmetries breaks. No, not at all. Not at all. No. Wait, why do you say that? Oh, I see. You're trying to use that explanation. Yes. No. That's still not the reason. It's still not the reason. The reason is that higher form symmetries are different than zero form symmetries. So first of all, let me persuade you that this doesn't imply the mass. Actually, imply a mass for the photon. And actually, the simplest way to say it is, what could it be? Right. So m gamma, it's some function of the mass of the monopole. It has to have units of mass. And it has to go to 0 when the mass of the monopole goes to infinity. And let's work in the world where say the electron is massless. Yeah, let's work in the world where the electron is massless. So there's actually no other mass scale in the problem. So this has to be 0, just by dimensional analysis. Yeah.
It's always a regulator. The theory always needs to be regularized at some scale, because otherwise they don't even be well defined. They're pretending that they continue doing everything.
Yeah, it could be the scale at which the coupling force can go down.
Let's UV complete it by SU2 gauge theory. Let's with an adjoint Higgs. So then there are monopoles, but they happen at the scale where you UV complete it. Yeah. So the mass of the monopole is the same as the UV completion scale in that example. Yeah. Okay, sorry, I wasn't complete. Yeah. No, with adjoint Higgs, yeah. So sorry, I didn't really intend this argument to be taken so seriously. So a slightly less cheap answer, which takes a little longer, is put the theory on a circle. Put the theory on a circle and ask. So in that case, there is Polyakov confinement, and then ask how does the mass of the photon depend on the radius? And in that example, in 2 + 1 dimensions, on the radius of the circle. In that case, you can see that it depends like this, and which, as you can see, goes to 0 when the radius of the circle goes to 0. So that's a slightly better argument. So this is argument 1, this is argument 2. Argument 3 is even cheaper. As Eduardo emphasized yesterday, in order to give the photon a mass, in order to break the symmetry, we need to add to the Lagrangian some operator that's not invariant under the symmetry, some charged operator. But the charged operators aren't local. So unlike the zero form case with pions, where you can add the charged operators to the Lagrangian and it changes the physics, here you just can't. So that's the important difference, and so that's why so even approximate higher form symmetries have exact consequences because of this. So once the higher form symmetry emerges, you can't get rid of it. So this means something slightly funny for the generalized Landau paradigm, which is, we usually think of the Landau paradigm as, we're interested in studying theories that have symmetry G microscopically, and then we worry about, whether G is spontaneously broken or not. Here, this fact that the consequences of higher form symmetries are more robust means that we also have to worry about emergent higher form symmetries, right? So in the phase diagram of the Torah code, there's a whole phase. So in this part of the phase diagram, the higher form symmetry, this U and V here, this isn't an exact symmetry, right? U is exact, but V is only emergent in this phase. So it's maybe not a perfect generalization of what we usually do, because we have to worry about emergence. Yes, that's right. Okay, so there are a few other very nice applications of this point of view. One of them, one I think that's quite nice, is to try to generalize what I said about the logic by which we derived Landau-Ginzburg theory for the zero form case, to try to generalize that to the higher form case, which leads to a funny kind of field theory where the degrees of freedom are functionals of curves, which I think is quite interesting, and from which, the real motivation for doing this is to answer this question that's come up several times of what is a gauge theory, right? This is some perspective from which we can, try to derive the structure of gauge theory without starting from a description that involves gauge redundancy. But maybe I won't say much about that. Okay. All right, so I think maybe in the last few minutes of today, I'm going to try to summarize. So, yeah, maybe we can play a game together. Let's list some kinds of phases of matter and see if we can understand them in terms of symmetry. I think, so I guess, maybe along the way to doing that, it's maybe I'll say a few more tools are we can think about subsystem symmetries. So this just means that the operators U are not fully topological. Not fully topological means that you can only deform them on some subspace of space-time. Maybe they only commute with the Hamiltonian and are not topological at all. So one example of an application of this is the phases that Fiona was talking about. Fracton topological order we can understand as spontaneous breaking of a subsystem higher form symmetry. I guess I should say anomalous higher form symmetry. Maybe it's worth mentioning that. So in these examples, the support of the operator was either on some planes, like in this line-on-planon example, or on a fractal, like in the Sierpinski example. In fact, there are models where the support of the symmetry has no structure at all, where it's like some Cantor set. Local translation invariant Hamiltonians, where there are symmetry operators whose support is basically an arbitrary subset of the space. It's a pretty crazy thing. Such a model was constructed by my student David Lin. It's a pretty exotic thing. Okay, so maybe that's everything I wanted to say about subsystem symmetry, since Fiona already did is doing a wonderful job of talking about fractons. So this is giving up. I forget. I think this was condition 4 maybe in my list of conditions, and then finally we can talk about non-invertible symmetries. Non-invertible symmetries, which is giving up need not form a group. Instead, let's label them by some label A. They satisfy a fusion algebra, so for example, TB could be the dagger of A. So the thing that you would want to be the inverse if they were unitary operators. But if over here, if on the right-hand side there's more than one term, so for example, we could say TA dagger, if it's 1 plus something, then these t's are not unitary. That's why I call them t rather than u. So the point being that these t's, this collection of t's, are topological, but not necessarily unitary. I don't know. I guess I talked to a bunch of you after yesterday's lecture, and everybody seems to be working on this subject, so I think I don't need to say elementary things about it, but maybe I'll just say that the kinds of topological order that we can understand as spontaneous symmetry breaking of ordinary higher form symmetries are always abelian, meaning that the operators that transport the anions are unitary, whereas spontaneous symmetry breaking of a discrete non-invertible symmetry it can give non-abelian topological order. Non-abelian topological order where the quantum dimensions are bigger than 1. There are anions whose quantum dimension bigger than 1. The quantum dimension is related to the number of terms on the right-hand side here. Okay, so yeah, this has many applications. Maybe I won't say anything about them except, maybe let me mention one thing about the meaning of the word non-invertible. So here's an example of a fusion algebra. Let's call it tau. So this is called the Fibonacci fusion algebra. So there's there are two generators. There's the identity and tau fuses with itself to 1 plus tau. You can see that it's called Fibonacci because this is, if tau were a number, it would be the golden mean if you plugged it into this formula, or maybe the conjugate of the golden mean. But notice the following thing. Tau times minus 1 plus tau, if I plug in this formula for tau times tau, is minus tau plus 1 plus tau is 1. Right? So actually tau is invertible. I can find an inverse of tau according to this multiplication rule. In what sense is this a system that has a topological operator satisfying this fusion rule? Does it nevertheless have a non-invertible symmetry? The answer is that this is not allowed. Is not allowed. The reason it's not allowed is because of this minus sign. So these n's, in fact, always have to be positive. Have to be what's it called? Positive integers. There's a preferred normalization, and that's because. So here's a picture of space-time. Symmetry operators, let's say a zero-form symmetry. Zero-form symmetries in 2 dimensions. Or some operators like that act on a constant time slice. But for many applications, and I think it's actually a very important consistency condition, we should also be able to insert the same operator extended in time, in which case let's think about periodic boundary conditions. In which case this describes a Hilbert space, so this is some symmetry operator L acting on the state. This instead describes a Hilbert space twisted by L, where when we go around the spatial circle, we come back to ourselves only up to the symmetry operation. And this should have an integer, should have, what do I mean? I mean a positive integer. This should have a non-negative integer dimension. And that's what, and so in particular, we can't put a minus sign there. Okay, so in the last minute, let's summarize. So here, let's list the apparent counterexamples, and then we'll stop and have a coffee break. And the next time we'll completely change perspective, and Eduardo will maybe argue with me less. I don't know. Hopefully not. Okay. So here's the. Let's think about phases. So topological insulators are characterized by the anomaly of the edge. So a topological insulator for symmetry G has a G anomaly of the edge theory. Topological order is spontaneous symmetry breaking of an anomalous p-form symmetry, anomalous higher form symmetry. Fracton phases is spontaneous symmetry breaking of, I guess I already wrote that up there, of some subsystem higher form symmetry. okay, there are other phases of matter in the world. A prominent phase of matter, which is difficult for what I've said, is for the Landau paradigm, is Landau's own Fermi liquid. Right, so this is a phase of matter which is it's gapless in a whole phase. There's a whole Fermi surface worth of gapless degrees of freedom. How do we understand this in terms of symmetry? It's not explained by any symmetry that I've talked about so far. The time is up is flashing. Okay. Maybe I'll just say it has a very large emergent symmetry, which is called a loop U1 symmetry. Okay. Yeah, maybe in the questions you can ask me about other examples. Maybe the last one I want to mention is, why is the graviton massless? I think this is a good question. I actually don't know the answer. Maybe somebody can tell me. Okay, so that's a good place to stop. Thank you for your patience. I haven't seen it. I think my best answer is the following. A context in which we can try to answer the question is the case where we actually understand what quantum gravity is, which is when it's living in an asymptotically anti-de Sitter space. In that case, we know that it can be described completely by an ordinary field theory, a field theory which is a conformal field theory in the UV. Certain kind of weird conformal field theory with large n and some special set of scaling dimensions, but nevertheless an ordinary field theory. And so we know that there's certain field theories where such a thing is described by ordinary Einstein gravity with some extra fields in anti-de Sitter space, which has gravitons, so it has massless gravitons. And I think it's fair to say that there's some useful notion which I want to call gravitational order that such a system has, which characterizes the fact that it's in a phase which has this holographic description. And maybe the way to characterize it is it's a generalization of topological order in the following sense, that both topological order and this other kind of thing describe error correcting codes, where the information about which state you're in is encoded redundantly in the wave function. And so I think that's one way to characterize why there's such a phase. And we certainly know that there are other phases of the same system where there's no graviton. So that's a case where we can kind of destroy the order. But to get to an explanation of why the graviton is massless, I don't know. Okay. Which symmetry do you mean?
It's one for symmetry, generalized one for
Really?
I can explain.
Okay,
Well,
interesting.
And then you can apply this out.
Cool.
So, for the linearized case, not for the
Uh-huh.
but I think it's enough to convince myself.
So you made this comment that the necessity of non-convertible symmetries implying non-ambiguous topological order. In this scenario, we still require symmetry.
Great. Yeah, that's a good question. I think so. I considered adding that qualifier here, but I think actually it's not necessary. I think there's a sense in which non-invertible symmetries are always anomalous. Okay, I'm not sure. Yeah, I'm not sure. Okay, thank you.